Okay, so now we're going to look at a special case of first order kinetic, which is the case in radioactive decay. Nuclear chemistry is the type of chemistry that studies reactions that are involved in the nucleus or the nuclear structure. And so we're going to look at something called a nuclide, which is basically just the atom written in this form, which you might remember from Chem 11 as representing the mass number on the top, that's the A, and then the Z represents the atomic number. X itself, of course, is just a symbol of that element. So remember that the atomic number, or Z, is actually the same as the number of protons, and the mass number, or A, is the sum of the protons and neutrons. Now, when you actually look at a plot of the number of neutrons versus the number of protons, there is a pattern associated with increasing number of protons or increasing atomic number given in blue. So that is the pattern of the stable nuclei. So in other words, they don't change to anything else. However, that's not the only nuclei that exists. There is this spread of all this green stuff right here. Now, the ones that are in blue are the non-radioactive nuclei, meaning that when you have them, they just stay as they are. They don't change. Whereas the radioactive one would decay into more stable isotopes. So you might start with something that's much heavier, has a lot of neutrons and protons, and they might release some of those protons and neutrons in the form of radiation. And we'll talk about what kind of radiation could happen. And then that would result in formation of a lighter and smaller nuclei, which are stable. So what we call a band of stability, or sometimes called a zone of stability, is just all the nuclei that are stable. And then everything else are the radioactive nuclei, which we call radioisotopes. The change from one of these radioactive nuclei into something that is not radioactive is what we refer to as nuclear reaction. This is just similar to the idea of a chemical reaction. You're going to need to have a balanced equation following the conservation laws. In this case, we're looking specifically at the mass number and making sure that the masses on the left add up to the same as the total of the mass on the right side. And then some of these nuclides turns out to have charges. They might be negative like the electron. They might be positive like the proton. So some of the charges on the left and the right have to be equal to each other. This table right here shows you some of the common types of radiation. So remember I said earlier that you can have a heavy nuclide that then decays into a lighter nuclide, which is the more stable form. So let me just show something like this. Heavy go to light, which is the more stable one, but then you also release some kind of radiation as a result of it. And the radiation is one of these forms right here. It could be others, but these are the most common ones. So sometimes you'll get something called an alpha particle, which is basically just a helium nucleus. You can have a beta particle, which is really just high energy electron. You can have positron. This particle is same mass as the electron, but then has a positive one charge. You can have the proton, neutron, and then you can have gamma ray, which is very high energy radiation in the form of electromagnetic waves. So here's an example. I'll just walk through it for you. So we have a reaction between an alpha particle, one of the ones we talked about earlier. That's the helium nucleus. And then with magnesium 25, and it produces a proton and a nuclide of another element. So it says identify the new nuclide that's produced. And so looking at the actual reaction, you're going to have to remember some of these things. Magnesium 25, remember that all magnesium is going to have 12 protons. So the atomic number is going to be 12. And so we write the nuclide in this form, Mg with the mass number of 25 and atomic number of 12. This is the alpha particle. It's a helium nucleus. It has 4 mass number and then 2 for the atomic number. And on the right side, it says it produces a proton. So a proton is written as hydrogen with a mass number of 1. And then we have our new nuclide that we have to figure out. And the calculation is pretty straightforward. You have to add the mass number on the left, 25. 25 plus 4 equals 29. So this is 1, so that one must be 28. And then this is 12 and 2, so that's 4. This is 1, so that must be 13. Okay, so then your new nuclide is X, 13, 28. And then you need to go to the periodic table to figure out what that 13 represents. Find that X here must be aluminum, because that's the element that has 13 protons. This will be an aluminum 28 isotope. And that's really how you would work through these kind of problems. Our interest really here is not necessarily to delve into the radiochemistry, but more particularly in understanding that radioactive decay, which is this process where something heavy becomes something lighter, it releases this radiation. And the decay process can be understood through first order kinetics. So the same type of kinetics that we've been learning in the prior lecture. In fact, each of these decay has a certain half-life, and the half-life follows the first order kinetics, so it's a constant every time. And depending on the type of decay that we're looking at, the half-life can be different amount of time. So you'll see in some of the questions that the types of decay that would be often used would be either alpha decay, that's when you produce one of those alpha particles, beta decay where you produce the electron, and then gamma decay where you produce the gamma ray, which has no mass at all, positron emission, or sometimes you might actually add electron to yourself, but because electron is negatively charged, you still lose some protons as a result of it. So if you remember that, that's the equation for first order integrated rate law. And we just repurpose that equation where now n sub t here represent the number of nuclide quantity of it currently, and then n sub 0 would be your nuclide initially. And then we also have this symbol lambda, which is our decay constant, but it's really the same idea as the rate constant that we're talking about. And so you can see that the half-life equation is the same, which is just 0.693 divided by the constant. In this case, we use lambda to represent the constant. What I'm going to do is just work through a problem here about radioactive decay, but then we're going to analyze it using that first order kinetics, okay? So it says here that 2760 cobalt isotope is decaying with a half-life of 5.27 years, and then it ends up producing a nickel isotope as a result, and then it's asking you a number of questions, so we're going to go through and analyze. Okay, so looking at the question itself, the first part of the question just says, what's the decay constant? That's just referring to the rate constant. So it's sort of asking, what's the rate constant for this particular radioactive reaction? We're going to use the half-life equation from first order kinetics, which is just T1 half equals to 0.693 over lambda. And so we're rearranging to solve for lambda. And our T1 half is 5.27 years. So if you do the calculation, you end up getting 0.131 per year. So remember that that's the unit of the rate constant for a first order reaction. The second part of the question asks for the fraction of a sample of the cobalt isotope that will remain after 15 years. So what it's saying is that, okay, after this radioactive process, there's going to be less of the cobalt 60. That makes sense, right? So how much of that will be there after 15 years? But they want you to express that number as a fraction of the original sample. So in other words, the original sample, of course, in our symbolism would be considered A naught, right? Or in the case of the radioactive sample earlier, we would just write it as N naught. We want to know what fraction of N naught is our cobalt isotope that is present after 15 years. I start with the first order rate law, and if you want to change all those A's into the N symbol, you can. And so we get ln of A over A naught equals negative KT. Again, the K could be changed to lambda here. A over A naught should then be equal to E to the power of negative KT because I'm removing the natural log here and changing it to exponential. And then finally, I move the A naught the other way. So then I'm solving here for A. So A should equal A naught times to the negative KT. And this is just the exponential form of the first order equation. The A naught has no number, so we'll just keep it as is, as a symbol. But the K was 0.131 per year that we solved that in question A. So I'm going to plug that in here. They're asking for 15 years, so we're going to put that for T. And then calculating that out gives us 0.139 A naught. Or you can answer it this way, N of T is equal to 0.139 N naught. It just tells you that after 15 years, what's left is only 0.139 of the original quantity of radioactive isotope. This, of course, could be expressed as a percentage. It would just be 13.9% N naught, okay? The last question says, how long does it take for a sample of the isotope to disintegrate to the extent that only 2% of the original amount remains? Now we want to know time instead of the amount that's left. So if you want to know time, start with the same first order equation, except that now we are solving for time, which would make it look like that. T is equal to ln of the A over A naught divided by negative K. We were told the A that we're looking for is 2% of A naught, which could be written as 0.02 A naught. And so that's what I've written here. The A naughts, of course, cancel. So it's just ln of 0.02, which is a negative number. That negative number is going to cancel with the negative 0.131 per year for the rate constant at the bottom, giving you 29.7 years. And you might look at this number and think, that is a long time, right? It takes 30 years for this cobalt isotope to decay. And this is something that decays with a half-life of 5.27 years. Think about some of those other ones that we were looking at before. Look at decay of that radioactive uranium. It's 10 to the 9 years, like a billion, right? So just imagine that, the amount of time that you have to wait before the quantity get reduced by half. So this is just some of the calculation to illustrate how we can apply the same kinetic to the idea of radioactive decay.